Welcome to this walkthrough of problem number 1739, building boxes. In this session, we'll dive into the problem, explore a brute force approach, and discuss its key insights. Let's get started. Imagine you are stacking boxes in a pyramid-like structure, where each level builds on the previous one. The first level is simple, it consists of just one box. For the second level, you add two more boxes, making the total 3 so far. The third level then adds 3 boxes, bringing the total to 6. This pattern continues, with the kth level containing exactly 1 plus 2 plus 3 plus k boxes. This sum of the first k natural numbers determines the total number of boxes up to that level. Now, given an integer n, the task is to calculate the minimum number of levels in this pyramid such that the total number of boxes is at least n. If the total exceeds n, the extra boxes are simply left unused. You need to figure out how many levels are required to meet or exceed n, and return that number as an integer. Let's look at an example to make this clearer. If the input n is 3, the output is 2. This is because, to have at least 3 boxes, you need 2 levels. Level 1 contains 1 box, and level 2 adds 2 more boxes. Together, 1 plus 2 gives us exactly 3 boxes. Since we reached the required number of boxes in 2 levels, the minimum number of levels is 2. Now consider a slightly larger input, where n is 10. For n equal to 10, the output is 4. This time, you need 4 levels to achieve at least 10 boxes. Level 1 starts with 1 box, level 2 adds 2 more, level 3 adds 3, and level 4 contributes 4 boxes. Adding these together, 1 plus 2 plus 3 plus 4, we get exactly 10. So, the minimum number of levels required is 4. Let's explore one more example, where n is 15. When n is 15, the output becomes 5. In this case, you need 5 levels to stack at least 15 boxes. Starting with 1 box at the first level, then 2 at the second level, 3 at the third, 4 at the fourth, and finally 5 at the fifth level, the total becomes 1 plus 2 plus 3 plus 4 plus 5, which equals 15. Here, the number of boxes matches n exactly, so the minimum number of levels is 5. Now, there are some important constraints to keep in mind. The value of n can range from 1 up to 10 to the power of 9, so the solution must handle very large inputs efficiently without running into performance issues. You also need to account for edge cases, such as when n equals 1, where only one level is required, or when the total number of boxes at the required levels exceeds n. In all such cases, the solution must return the correct number of levels while ensuring the computation remains optimal even for the largest possible values of n. To solve this problem, we can start by considering a brute force approach. The idea here is to simulate stacking boxes level by level, where each level requires a triangular number of boxes, 1 for the first level, 3 for the second, 6 for the third, and so on. By iteratively calculating these triangular sums, we can determine when the total number of boxes matches or exceeds the given number, n. However, this approach becomes computationally expensive for large values of n because it requires repeatedly summing these numbers level by level. To address this inefficiency, we turn to an optimized mathematical approach. The key observation is that the number of boxes in the first k levels forms a sequence of triangular numbers, with the kth triangular number given by the formula t, k, equals k asterisk, k plus 1, / 2. Using this, we can calculate the cumulative sum of triangular numbers up to level k with the formula s, k, equals k asterisk, k plus 1 asterisk, k plus 2, / 6. This allows us to compute the total number of boxes for any given k directly, eliminating the need for iterative summation. To find the smallest k such that s, k, equals n, we use binary search, which efficiently narrows down the solution space and avoids unnecessary computations. There are a few key insights that make the mathematical approach so powerful. First, triangular numbers grow quadratically, and their cumulative sums grow cubically. This relationship allows us to compute results efficiently using mathematical formulas instead of iterative calculations. Second, binary search dramatically reduces the number of potential k values we need to check, making the process much faster than a level-by-level simulation. Finally, we can precisely adjust the height of the final level to ensure the total number of boxes equals n, minimizing any extra boxes. These observations led us to choose the optimized mathematical approach as our strategy for solving the problem. By leveraging the formula for the sum of triangular numbers, we reduced the problem to a binary search over a small range. This approach is not only efficient but also provides a deeper understanding of the problem structure. Comparing this to brute force, the brute force method is straightforward but suffers from inefficiencies due to repeated summation, with a time complexity of O(n). In contrast, the mathematical approach scales much better with a time complexity of O log n. Other alternatives, such as dynamic programming, could store intermediate results, but the overhead is unnecessary given the simplicity and efficiency of the mathematical method. For these reasons, the mathematical approach is the most suitable choice, striking the perfect balance between clarity, efficiency, and scalability. To understand the problem, imagine building a pyramid using boxes. Each level of the pyramid requires a triangular number of boxes. For example, the first level needs 1 box, the second level requires 3 boxes, the third level takes 6 boxes, and so on. These triangular numbers are calculated using the formula level asterisk, level plus 1/2. The goal is to determine how many complete levels can be formed using a given number of boxes, n. To solve this, we start by initializing a few key variables. First, level is set to 0. This will count the number of levels we can fully build. Next, remaining underscore boxes is initialized to n to track how many boxes are left after constructing each level. Finally, we use a variable called boxes underscore needed to calculate the number of boxes required for the next level as we iterate through the process. With these variables in place, we can begin constructing the pyramid level by level. Now, we use an iterative approach to build the pyramid one level at a time. A while loop ensures we continue as long as the number of remaining underscore boxes is greater than or equal to the boxes underscore needed for the next level. Inside the loop, the first step is to calculate the boxes underscore needed for the current level using the triangular number formula, level asterisk, level plus 1/2. Once we know how many boxes are required, we check if we have enough boxes to build that level. If remaining underscore boxes is sufficient, we subtract boxes underscore needed from remaining underscore boxes and increment the level by 1 to move on to the next. However, if the remaining underscore boxes are no longer enough to complete the next level, the loop exits because no further complete levels can be built. By the end of this process, the level variable will hold the maximum number of complete levels we were able to construct. This algorithm is efficient because it uses the triangular number formula to quickly compute the boxes needed for each level and terminates as soon as we run out of boxes, avoiding unnecessary calculations. This algorithm relies on simple variables to manage its state, making it both efficient and memory-friendly. The key variables are level, which tracks how many levels have been completed, remaining underscore boxes, which keeps count of the boxes left, and boxes underscore needed, which calculates the number of boxes required for the next level. Since the problem only involves sequentially building levels and doesn't require tracking past states, there's no need for arrays or other data structures. This keeps memory usage minimal. Let's walk through an example to see the algorithm in action. Suppose we have n equals 10 boxes. For the first level, we calculate boxes underscore needed equals 1. Subtracting this from remaining underscore boxes leaves 9 boxes, and the level is increment to 1. For the second level, boxes underscore needed equals 3. Subtracting 3 from 9 leaves 6 boxes, so we increment level to 2. For the third level, boxes underscore needed equals 6. Subtracting 6 from 6 leaves no boxes, and we increment level to 3. For the fourth level, boxes underscore needed equals 10, but there are no boxes left, so the loop terminates. The output is level equals 3, indicating that 3 complete levels can be built with 10 boxes. Analyzing the complexity, the algorithm is highly efficient. The time complexity is approximately O(n), as the triangular number formula ensures that we calculate the required boxes for each level in constant time, and the loop runs until the sum of triangular numbers approaches n, which grows proportionally to the square of the number of levels. The space complexity is O(1), because only a constant number of variables are used, with no arrays or additional data structures. This makes the algorithm suitable for handling even large values of n. Several edge cases are worth noting. For n equals 0, no levels can be formed, so the output is 0. For inputs like n equals 6, where the number of boxes is exactly enough for 3 levels, the algorithm correctly identifies the maximum number of levels. For large inputs, the algorithm remains efficient due to its n complexity. Lastly, for a single box, n equals 1, only one level can be formed, which the algorithm handles seamlessly. Together, these considerations ensure the algorithm is robust and handles a wide range of scenarios effectively. This solution involves calculating the minimum number of boxes required to form a pyramid structure with n boxes. The problem is essentially about building levels of pyramids where each level requires a triangular number of boxes. The function triangular x is a helper function to compute the triangular number for a given x, using the formula x plus 1/2. This is a fundamental step since triangular numbers define the number of boxes needed for each level. We start by determining how many full base levels can be formed with the given n boxes. We incrementally add levels, calculating the total boxes used, until adding another level would exceed the given number of boxes n. This process gives us the maximum number of full base levels that can be formed, and total_boxes keeps track of how many boxes have been used so far. Once the full base levels have been formed, there might be some remaining boxes left. These boxes are used to complete the next level partially. The remaining variable tracks how many boxes are left after forming the full base levels. To calculate the minimum additional boxes needed to cover the remaining boxes, we incrementally test adding more boxes to the next level until the triangular number for those boxes is at least equal to the remaining count. This ensures we are forming the smallest possible partial level to use up the boxes efficiently. Finally, the result is the sum of the boxes used in the full base levels and the additional boxes required to cover the remaining boxes. The function returns this total as the minimum number of boxes needed to form the pyramid structure with n boxes. Here, we start by defining a method named minimum boxes that calculates the minimum number of boxes required to build a pyramid-like structure that holds exactly n boxes. To assist with this, we include a helper method called triangular, which computes triangular numbers using the formula x plus 1/2. This formula is crucial because triangular numbers represent the total number of items in a complete triangular arrangement with x rows. Next, we initialize two variables, base levels, to track the number of full levels in the pyramid's base, and total boxes, to keep a running total of the boxes used so far. Using a while loop, we calculate the maximum number of full base levels that can fit within the given n boxes. The loop continues as long as adding another level, represented by triangular, base levels plus 1, does not exceed n. With each iteration, we increment base levels and add the corresponding triangular number to total boxes. After exiting the loop, we calculate the remaining number of boxes, that still need to be placed to reach n. For this, we subtract total boxes from n. Finally, we introduce additional boxes, which will count the extra boxes needed to cover this remainder. To determine the minimum number of additional boxes required, we use another while loop. This loop checks if the triangular number for the current additional boxes is less than the remaining boxes. If so, we increment additional boxes until the condition is met. Once we have the correct count of additional boxes, we return the total number of boxes used, which is the sum of the triangular number for base levels and additional boxes. It's important to note that the triangular method is defined as private here, encapsulating it within the class. This ensures that it serves its purpose solely as a utility function for the minimum boxes method. By organizing the code in this way, we maintain clarity and modularity, making the solution efficient and easy to understand. To solve this problem, we start by initializing three key variables. The first is base_levels, which keeps track of how many complete levels of boxes we've built. Initially, this is set to 0. The second variable is total_boxes, which represents the total number of boxes used so far, also starting at 0. The last variable is remaining, which is set to the input value n, in this case 10, and represents how many boxes are still needed. Next, we calculate the maximum number of full base levels we can build using the helper function triangular x. This function gives us the triangular number for x, or the total boxes required for x levels, calculated as x times x plus 1 divided by 2. To determine if we can add another base level, we check if the total boxes used so far plus the boxes in the next level is less than or equal to n. For the first iteration, setting base underscore levels to 1, the triangular number is 1, and the total boxes become 1. For the second iteration, with base underscore levels set to 2, the triangular number is 3, and the total boxes increase to 4. On the third iteration, the triangular number for base underscore levels of 3 is 6, bringing the total boxes to 10. This equals n, so we stop here as no more base levels can be added. With the full base levels determined, we now calculate the remaining boxes needed. Subtracting the total boxes used, 10, from n, which is also 10, leaves us with 0 remaining boxes. Since no additional boxes are needed, the result is simply the triangular number for the maximum full base levels, which is triangular, 3. Using the formula, this equals 6. Therefore, the final output for this example is 6. In this second example, we follow the same steps but with n set to 15. First, we initialize the variables. Base underscore levels and total underscore boxes both start at 0, while remaining is set to 15. Using the triangular function, we calculate the maximum full base levels we can build. For base underscore levels of 1, the triangular number is 1, and the total boxes become 1. For base underscore levels of 2, the triangular number is 3, increasing the total boxes to 4. For base underscore levels of 3, the triangular number is 6, bringing the total boxes to 10. Finally, when base underscore levels is 4, the triangular number is 10, and the total boxes increase to 20, which exceeds n. Since that's too many boxes, we revert back to base underscore levels of 3, where the total boxes remain 10. Next, we calculate the remaining boxes needed. Subtracting the total boxes used, 10, from n, which is 15, gives us 5 remaining boxes. To account for these, we need to find the smallest number of additional boxes that can cover this remainder. We check successive values of additional underscore boxes using the triangular function. For additional underscore boxes of 1, the triangular number is 1, which is too small. For additional underscore boxes of 2, the triangular number is 3, still too small. For additional underscore boxes of 3, the triangular number is 6, which is sufficient to cover the remaining 5. Finally, we compute the result by adding the triangular number of the base levels to the additional boxes needed. The triangular number for base underscore levels of 3 is 6, and adding 3 gives a result of 9. This means the output for this example is 9. Now let's consider the third example where n is 20. As before, we initialize the variables. Base underscore levels and total underscore boxes are set to 0, and remaining is set to 20. We calculate the maximum full base levels we can build using the triangular function. For base underscore levels of 1, the triangular number is 1, and the total boxes become 1. For base underscore levels of 2, the triangular number is 3, increasing the total boxes to 4. For base underscore levels of 3, the triangular number is 6, bringing the total boxes to 10. Finally, for base underscore levels of 4, the triangular number is 10, and the total boxes increase to 20. This matches n exactly, so we stop here as no more base levels can be added. Since the total boxes used equals n, there are no remaining boxes to account for. This means the result is simply the triangular number for the maximum full base levels. For base underscore levels of 4, the triangular number is 10. Therefore, the final output for this example is 10. To analyze the time complexity of our solution, we start by examining the first loop, which determines the maximum number of full base levels that can be formed. Here, the while loop runs as long as the total number of boxes, including the next triangular number, does not exceed n. The triangular function, which calculates the xth triangular number using the formula x asterisk, x plus 1, // 2, grows quadratically with respect to its input. This means that the total number of iterations in this loop is proportional to the square root of n, since the cumulative sum of triangular numbers up to k is approximately proportional to k caret 3. Each iteration performs constant-time arithmetic operations and calls the triangular function, which is also O1. Thus, this loop contributes a time complexity of O, sqrt, n. In the second loop, we determine the minimum number of additional boxes required to complete the structure. Here, the loop continues as long as the triangular number of additional boxes is less than the remaining boxes that need to be added. Since the triangular number grows quadratically, this loop also runs approximately O, sqrt, remaining iterations. In the worst case, where remaining is as large as n, the complexity of this loop is also O, sqrt, n. Now, let's combine the contributions of both loops to determine the overall time complexity. Since the loops operate independently, their complexities are additive. This means the total time complexity is O, sqrt, n, plus O, sqrt, n, which simplifies to O, sqrt, n. Moving on to space complexity, the algorithm only uses a small number of integer variables, such as base underscore levels, total underscore boxes, remaining, and additional underscore boxes. No additional data structures, such as arrays or lists, are used. The triangular function itself is a simple arithmetic operation and does not consume any extra memory. As a result, the space complexity of this solution is constant, or O1. This reflects an efficient use of memory, irrespective of the input size. When comparing this optimized solution to a brute force or naive approach, the benefits become clear. A naive solution would involve iterating through all possible combinations of base levels and additional boxes, incrementally summing triangular numbers to check if the total matches n. This approach requires repeatedly performing calculations over a much larger range of values, leading to a time complexity of O(n). In contrast, the optimized solution takes advantage of the quadratic growth of triangular numbers to dramatically reduce the search space. By focusing only on the relevant ranges, the optimized solution achieves a time complexity of O, sqrt, n, making it significantly faster and more efficient than the naive approach. Looking at the best, average, and worst-case scenarios for this algorithm, we see that the time complexity remains consistent. In the best case, the input n is such that the full base levels already perfectly match n. In this case, the second loop does not execute at all, and the complexity remains O, sqrt, n. On average, both loops execute approximately O, sqrt, n iterations each, so the overall complexity is still O, sqrt, n. Even in the worst-case scenario, where the second loop for additional boxes runs the maximum possible iterations, the total complexity does not exceed O, sqrt, n. This consistency across all cases demonstrates the robustness of the algorithm. Finally, let's justify the time complexity mathematically. The kth triangular number is given by the formula k asterisk, k plus 1/2, which grows as O, k squared. The sum of the first k triangular numbers is proportional to O, k cubed. To cover n boxes, the number of base levels k must satisfy O, k cubed, is almost equal to n, which implies that k is almost equal to O, n caret, 1/3. However, the outer loop runs proportional to the square root of the total boxes, or O, sqrt, n. For the second loop, which searches for the additional boxes, the number of iterations is approximately O, sqrt, remaining. In the worst case, where remaining is as large as n, this also contributes O, sqrt, n. Combining these results, the overall time complexity of the algorithm is O, sqrt, n. Since no extra space is used beyond a few integer variables, the space complexity remains O1. When tackling this problem, there are several common mistakes to watch out for. First, ignoring constraints can lead to issues, especially with edge cases like very small or very large input values. Consider scenarios such as n equals 0 or n equals 10 to the power of 6. Forgetting these can result in runtime errors or incorrect outputs. Another frequent mistake is misjudging complexity. For instance, repeatedly calculating triangular numbers with brute force instead of storing them can lead to redundant computations, which unnecessarily increases time complexity. Off-by-one errors are another trap to avoid, especially in iterative calculations like summing triangular numbers. Developers might accidentally overshoot or miss a term by not verifying loop conditions carefully. Additionally, floating-point precision errors can arise when using mathematical equations, such as solving for n with the quadratic formula. For large numbers, this can lead to inaccuracies, so it's better to stick to integer arithmetic when possible. Finally, overcomplicating the problem by introducing recursion or complex data structures can add unnecessary overhead. Often, a simple iterative solution works just as well and is less prone to bugs. Now, let's consider some key insights for interviews. Recognizing recurring patterns is crucial in problems involving triangular numbers, stacking, or summation. These problems often follow clear mathematical structures, and spotting these patterns early can save valuable time. Clear communication is equally important. If you start with a brute force approach, explain your reasoning and discuss why it works. Then, demonstrate how you identify inefficiencies and plan to optimize. This iterative problem-solving approach is something interviewers value highly. Speaking of optimization, one way to improve efficiency is by using the formula n times n plus 1 divided by 2 for direct computation of triangular numbers, instead of looping. This approach avoids unnecessary calculations and reduces time complexity. For larger inputs, binary search can be a powerful tool to efficiently find the maximum level or number that satisfies a condition. Finally, exploring related problems can help deepen your understanding. For example, LeetCode 441, Arranging Coins, involves a similar triangular number concept. Problems like climbing stairs, candy, and ways to split array into 3 subarrays also share themes like summation, constraints, and partitioning, offering valuable practice opportunities. To wrap up this section, let's explore some alternative approaches to solving problems like this. The most efficient method is often a mathematical formula, such as n times n plus 1 divided by 2. This eliminates the need for loops and achieves constant time complexity, O(1). However, for very large values of n, you need to be cautious about integer overflow and ensure your implementation handles it correctly. Another approach is binary search, which is particularly useful when you need to find the maximum level or number that meets a given condition. Binary search reduces the time complexity to O log n, though it requires a slightly more complex implementation. Lastly, dynamic programming can be helpful for variations of this problem where constraints depend on previous levels or states. That said, dynamic programming may introduce unnecessary overhead if the problem can be solved with simpler methods. Each approach has its trade-offs, so it's important to choose the one that best fits the specific problem and its constraints. We've reached the end of our walkthrough for problem number 1739, building boxes. Today, we reviewed a brute force approach and the key insights for solving this problem. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!